Hi everyone. So in this short course, we'll describe Monte Carlo algorithms not for light transport, but for the physics of thermal diffusion, electrostatics, and even fluid mechanics on 3D models that have extremely complex geometry. This talk will be evenly split between Bailey Miller and myself. Bailey is currently doing his PhD at Carnegie Mellon with Yanis Giolakis. I did my PhD at CMU as well under Keenan Crane, and I now work in the high fidelity physics group at NVIDIA. Both Yanis and Keenan have been key collaborators on a lot of the ideas that we'll present today. So, to set the stage, consider a modern ray tracer such as the RTX renderer in NVIDIA's Omniverse, which, in my opinion, is a pretty amazing piece of technology for two reasons. First, it can simulate the physics of light transport in scenes with highly detailed geometry. And second, it provides instantaneous feedback even when the scene changes, which really helps to speed up the design cycle if we need to modify the lighting, materials, or geometry. Coupled with machine learning frameworks like DLSS, today we can even denoise and supersample these Monte Carlo renderings in real time. So, altogether, I think it's fair to say that this technology for photorealistic image generation has revolutionized industries like entertainment and industrial design, and it's also having a growing impact on computer vision for applications such as 3D reconstruction from images, as well as on simulation engines for robotics tasks, such as training self driving cars in photorealistic digital environments. However, the physics of light transport isn't the only type of physics we care about. For instance, being able to simulate thermal conduction, structural mechanics, and electromagnetism is critical to many engineering applications. At their simplest, these phenomena are described by partial differential equations such as the Laplace equation, which implicitly describes a function in terms of its derivatives. Concretely, the Laplace equation says that if we're given some data on the boundary, such as temperatures, displacements, or colors, then solving for explicit function values smoothly interpolates this boundary data into the interior of the domain. Now, even though this equation is a pretty simple physical model, it already has several real world applications. So, for instance, in the design of integrated circuits, we can use it to study the on chip temperature to make sure that our circuit boards don't dissipate too much power. But this also means that we require scalable and accurate physics solvers to help us understand how all the micro to nanoscale geometry on a circuit board impacts electric potentials and temperature. Similarly, to build efficient data centers, we need to understand how all the wiring and cooling in a building information model impacts the thermal response of the data center. And in many more such cases throughout science and engineering, it's really this interplay between complex geometry and even some relatively simple physics that is central to computer aided design and manufacturing. Now, in recent years, our ability to model, capture, and generate complex geometry has improved drastically. But even after decades of developing methods for simulating physics, PDE solvers, ranging from finite difference schemes to spectral methods, all still struggle to handle the detailed geometry that we can visualize today. And this is because all of these numerical methods share a common characteristic. They use a finite dimensional approximation to compute the PDE solution. So, using the finite element method as an example, the typical pipeline is to first dice up our domain into tiny pieces to form a mesh. We then use the mesh to find some basis functions phi sub I, which we further use to assemble and invert a linear system to solve a Laplace equation in some weak sense. But if we do things this way, then we'll necessarily have errors both due to the approximation of geometry as well as the approximation of functions. The bigger challenge, however, is that geometry found in the physical and natural world can be extremely complex. But we're nowhere near simulating this level of geometric complexity because it takes an extremely long time to mesh. And in general, mesh generation is just a very memory intensive process that's also difficult to parallelize. Since most of the geometry found in the wild also contains degenerate inputs, in many cases it's just impossible to run our solvers without some extremely time consuming manual cleanup or pre processing. This example actually shows an extreme case. In reality, even just a single bad element can cause a whole simulation to blow up. A bad mesh can also provide a false sense of reality. So here is an example where geodesic distances are computed using a finite element solver on a mesh with skinny triangles. Notice that the FEM solution actually doesn't match the reference at all because of poor triangle quality. And so if we spend all of our time converting our domain into a mesh that's simulation ready, then that completely defeats the purpose of having fast or accurate finite element solvers that are currently the de facto tools for simulating high fidelity physics. In fact, engineering design cycles today are bottlenecked not by modeling or visualization, but precisely by this need for a high quality discretization for simulation. Now, one approach is to keep improving meshing algorithms to handle more complex inputs. And to be fair, algorithms for robust meshing have gotten really good in recent years. But meshing and model cleanup more generally really seem like problems that may never be completely solved. This is because even with the latest and greatest tools for volumetric meshing, we still run into situations where it can take hours to generate a tetrahedral mesh, even for models with some relatively simple geometry. And even if the meshing algorithm terminates, it can come at a cost like missing important surface detail, like vessels in a 3D model of the heart, that completely change the meaning of a PDE solution, modeling, for instance, oxygen or blood flow. And so, to faithfully simulate nature and the physical world, we must find ways to handle a much greater level of geometric complexity than what our solvers are currently capable of. So, back in the 90s, people ran up against the same problems in rendering. If we wanted to make a photorealistic image, given a description of the geometry, materials, and lights in a 3D scene, then we would use something called finite element radiosity, where we make a mesh of the scene, build a large linear system, and solve for illumination everywhere in the scene by inverting the linear system. Now, this idea fell out of fashion for many reasons, but in large part because robust meshing is just a really hard problem. Instead, the rendering community now uses Monte Carlo methods for photorealistic rendering that recursively shoot rays that bounce around the scene. So, in place of meshing and global finite element solves, we now use repeated random sampling to intersect the domain boundary with a ray, which is a lot easier to do in practice and a lot more robust to triangle quality. We then simply average the results from n different processors to get our final estimate for the illumination in the scene. Now, because of the shift to Monte Carlo methods, modern photorealistic rendering today can handle scenes with immense geometric complexity. But maybe what's even more amazing about this technology is that it just works irrespective of what scene we throw at it. So, as an example, here's a rendering of NASA's Curiosity Mars rover. In fact, it's not a rendering of an official engineering schematic, but rather an amateur model that we downloaded off the web. And it looks pretty compelling, right? In fact, this is sort of the state of the art in rendering. No matter what model you throw at it, it just works and you even get some instant feedback. But what if we need to predict something beyond appearance? So, for instance, NASA's own guidelines essentially tell engineers that thermal simulation is really important not just at the very end, but throughout every stage of the design phase where you want to know what's going on with the system physically and not just what it looks like visually. And so, a big focus of this course will be on how we can make simulation described by Laplacian PDEs more like Monte Carlo rendering, so that we can simply load up a complex model and hit go without worrying about meshing, basis functions, or global solves. The primary workhorse of our approach will be a little known Monte Carlo algorithm from the 1950s called walk on spheres, which, like ray tracing, works by performing recursive random walks in an n dimensional scene to solve Laplace type PDEs. Geometrically, the basic walk on spheres algorithm relies on performing distance queries in place of ray intersections, which are also a lot easier to do in practice than generating simulation ready volumetric meshes. Now, we'll generalize this solver in multiple ways over the course of this talk, but to first give a sense of what this solver is capable of, here we perform a thermal study on the same Curiosity rover from before, using a deferred shading approach to compute temperature values only at visible points in screen space. So this means that just like Monte Carlo rendering, we can also focus all our computational effort only on local regions of interest, such as the zoom-ins on the surface of this rover, rather than computing the solution on the entire domain like a traditional grid-based solver. Historically, this type of thermal modeling has been difficult to integrate into the design phase precisely because of finite element meshing, which completely destroys surface detail on the Mars rover if we try to tetrahedralize this model. In this case, we actually run out of memory completely if we allocate more processing time to state of the art meshing tools. The Monte Carlo approach eliminates these bottlenecks and demonstrates how physical simulation can be made more like rendering in terms of progressive and view dependent feedback. Now, to be candid, I want to point out that these are still early days for Monte Carlo PDE solvers, and these methods may never be applicable for certain types of simulation that are better suited for traditional solvers. But given how far Monte Carlo methods have brought us in simulating realistic illumination, I think it would be crazy not to try to build something like a ray tracer for physical problems beyond light transport that require solving Laplacian PDEs in complex geometric domains. Okay, so that was the sales pitch for using Monte Carlo methods in geometry processing and simulation. The remainder of this talk is structured as follows. So first, we'll review the basics of Monte Carlo and show how to apply its key principles such as estimation of integrals, sample generation and bias to the Laplace equation using walk-on spheres. We'll then discuss how to generalize walk-on spheres to solve Poisson equations and to handle a broader range of boundary conditions. In these sections, we'll also show how to apply a fundamental concept in Monte Carlo called importance sampling. We'll then provide an alternative perspective of walk-on spheres as an algorithm for simulating different types of Brownian motion. This perspective will help generalize the solver to an even larger class of problems. Since Monte Carlo methods produce noisy results, we'll also spend some time discussing variance reduction, and then we'll wrap up the course by evaluating the Monte Carlo approach, discussing some recent work, as well as future directions.
Many of our slides in this section are based on those from Keenan Crane and Gautam Iyer's new Monte Carlo course at CMU. Thank you, Keenan and Gautam. The Monte Carlo methods we're going to discuss today are a special type of algorithm that uses repeated random sampling to arrive at an approximate solution to difficult computational problems. These algorithms turn out to be broadly useful for a range of numerical problems, including integration, which will be the main focus of today. Not all randomized algorithms are Monte Carlo methods, however. Another class of randomized algorithms are Las Vegas algorithms, which similarly use repeated random trials, but always arrive at the same exact solution. For instance, randomized quicksort will always return the same sorted list. To get a flavor of what Monte Carlo methods entail, let's start with a motivating example. Let's say you want to sell custom-shaped cookies online, and you need to set the price based on the area of each cookie. So how do you go about computing the area of an arbitrarily shaped cookie? For simple shapes, we could just use analytic formulas, or even divide the cookie up into shapes that we know how to measure. But as the shape becomes more complex, the area becomes less trivial to compute, and very quickly we arrive at cookie shapes which are hard to decompose into elementary shapes. An alternative approach to measuring area is to approximate the area by throwing darts. So specifically, we place our cookie on a plate whose area is easy to measure, and then next we throw a bunch of darts at the plate, and we count how many of them hit the cookie. The percentage of darts which hit the cookie represent the portion of the plate which the cookie occupies, and this gives us a really simple way to compute area. We just multiply the occupied portion of the plate by the total plate area. This algorithm works for any shape, and so we can use it to measure the area of any cookie. With this toy example, we can get a sense of the strengths of Monte Carlo methods. For instance, the algorithms are extremely simple. So to measure the area, we just needed to know how to throw a dart and how to compute a fraction. And even though the estimate of area is approximate, if we throw enough darts, we eventually will obtain an estimate of area with a very high degree of precision. Finally, these algorithms are easy to parallelize, since there is nothing that's stopping us from throwing many darts simultaneously. But why are we throwing darts at cookies in the first place? Well, a wide range of problems, from light transport to thermal conduction, can be framed as these types of integration problems, which have analogous Monte Carlo dart throwing algorithms. There are usually three parts to solving these problems. First, we have to write down a mathematical description of our problem. Then, we have to convert that problem to an integral. And finally, we have to evaluate the integral. And we'll apply this framework to partial differential equations today to see how we can build Monte Carlo PDE solvers. But first, let's understand this last step to see why we'd want to reframe problems as integration problems in the first place. So, for those who haven't worked with integration in practice before, don't stress about whether or not you remember your integration tricks from high school or college calculus course. In practice, analytic integration won't be useful in our setting. Even very simple-looking expressions often don't have any representation in terms of elementary functions. Instead, one alternative is to use a numerical method such as quadrature to evaluate the integral. Quadrature divides the domain into discrete intervals and approximates the integrand on each interval with a constant function. The integral can then be approximated as a sum over the area of all these rectangles. And this seems great, so what's the catch? Well, to use quadrature in higher dimensions, we have to discretize the domain with higher order voxels, and this leads to an exponential increase in the number of voxels as dimension increases. Aside from the computational costs, quadrature is also limited by aliasing effects. So while discrete approximations capture the smooth integrands reasonably well, oscillatory or spiky functions will lead to poor approximations. The Nyquist-Shannon sampling theory does say that we will avoid aliasing as long as the sample rate or the size of our intervals are adapted to the highest frequency. Yet not every function has the highest frequency, and in these cases, quadrature will likely fail completely. These sort of spiky or high frequency functions are not just pathological cases, they're the norm in real world systems. In this photograph, for instance, we see discontinuities from the bridge acting as a mask on the background. We see high frequencies from all the buildings on the skyline, and spikes from the bright light sources and car headlamps. And yet, modern Monte Carlo rendering techniques can accurately synthesize images of this complexity, which amounts to integrating over all of these challenging features. So how is it that Monte Carlo methods can avoid the limitations of quadrature? The central idea behind Monte Carlo integration is to replace our deterministic samples of the integrand with random sample points. Along the x-axis, all of these black points are uniformly sampled in the domain of integration. At each sample point, we evaluate the integrand, and then we take the average of the integrand values across all n samples. Finally, we multiply by the total volume of the domain. Really, all we're doing in 1D is estimating the integral as a rectangle whose width is the length of the domain and whose height is the average function value. This approach is surprisingly simple, and yet it has many useful properties. For example, unlike quadrature, we don't need to choose the number of quadrature points in advance. We can continue to add more and more sample points to update a running estimate of the integral. Importantly, this approach also overcomes the two main limitations of quadrature. So first, we remove a dependence on dimension, since our cost is proportional to the number of samples we take. And second, by choosing our samples randomly, we removed any fixed highest frequency from our evaluation. In other words, every part of the domain has some probability of being sampled and evaluated by the Monte Carlo estimator. But how do we know that this Monte Carlo estimator is correct? And what does correctness even mean here? Well, our Monte Carlo estimator is a random variable, since it's just a function of random samples, and so we can analyze its expected value. Recall that expected value is just the value that a random variable will take on average. So for a discrete random variable x, this is the sum over the product of the probability and the value of each outcome. In the continuous case, this becomes an integral over a continuous space of outcomes. So we say that a Monte Carlo estimator is unbiased and hence correct if its expected value is equal to the true integral. And this is a really strong definition because it will hold for any number of samples. Even if we take a single sample, we expect that the expected value of the estimator will equal the true integral. A slightly weaker definition of correctness is consistency, which says that the estimator approaches the true integral as the number of samples increases. And finally, we say that an estimator is biased if it converges to some value that is not the true integral. We can verify that the Monte Carlo integral estimator is in fact unbiased with a simple proof. So starting from the definition of the estimator, we can apply linearity of expectation and move the expected value inside the sum. Next, the definition of expectation gives us an integral over the product of f and p. And since p of x is a uniform distribution, we can move it outside of the integral in the sum where it cancels out with the volume term. Thus, our expected value has been reduced to the true integral, and this implies that our Monte Carlo estimator is unbiased. While this shows that our estimator is correct in a formal sense, there's still much more to Monte Carlo integration that we need to be careful about. For instance, computers operate on floating point numbers, and so we need to make sure that our algorithms are numerically stable. We also mentioned earlier that Monte Carlo methods are potentially powerful because we can evaluate them in parallel. Yet there are several challenges in parallelizing, such as effectively evaluating an expensive integrand in a GPU implementation. More generally, theory and practice often go hand in hand when developing these Monte Carlo integration techniques. The practical obstacles often motivate novel mathematical formulations. For example, a very large set of Monte Carlo sampling techniques have been developed specifically to enable fast rendering on GPUs. So now that we've seen why Monte Carlo integration is a useful computational tool, let's see how we can express partial differential equations as integrals, and how to develop estimators for these integrals. First, we'll review the Laplace PDE. Then, we'll reformulate the Laplace PDE as an integral equation. And finally, we'll develop a Monte Carlo estimator for this integral. Recall that the Laplace PDE with Dirichlet boundary conditions takes a set of given values on the boundary and interpolates them to the interior as smoothly as possible. The smoothness is enforced by restricting the Laplacian of u to be 0 on the domain. Meanwhile, we constrain u to be equal to g on the boundary so that our function is actually interpolating the boundary data. Formally, the Laplacian is defined as a sum of second derivatives, or as the divergence of the gradient. More intuitively, though, the Laplacian acts as a difference between a value at a point x naught and the average value over a small sphere around x naught. So when the Laplacian is 0, we're saying that the solution at a point x naught is equal to the average of its neighbors. So given this interpretation of the Laplacian, what can we say about the behavior of functions whose Laplacian is 0 everywhere? We call these functions harmonic functions, and they have a special property that the value at a point x and the average over a sphere centered on x are equal. And this integral holds for any sphere around x that's contained inside of a domain, since the Laplacian will be 0 everywhere inside of these spheres. We therefore have an integral representation of the solution to a Laplace PDE. So the next step is to ask whether we can evaluate this integral with a Monte Carlo estimator. If we apply the basic Monte Carlo estimator from the previous section, we obtain an estimator for the mean value integral where the volume terms cancel out. We can evaluate this estimator by sampling points uniformly on the sphere and estimating the solution at each sample point. We use the same mean value estimator to estimate the solution recursively at the sample points, but unfortunately there's a problem with this approach. Every time that we estimate the solution, the estimator branches out to n new estimators. So after only 16 steps, a 3-sample estimator that's using this approach will require over 43 million recursive values to be estimated. And this is a huge memory and computational overload. And in fact, it's not tractable. So in order to actually make this approach tractable, we need to avoid branching. The easiest way to avoid this branching is to use only a single sample to estimate the mean value integral. Therefore, at each step, we choose the largest empty sphere around the current point, and then sample a single point on that sphere. Eventually, we terminate the walk when the sample point lands within an epsilon distance from the boundary, which we call the epsilon shell. Within the epsilon shell, we can approximate the value of the solution u in the domain with the value of the Dirichlet boundary condition g. And this is the complete walk-on-spheres algorithm. It's so simple that the high-level logic can be implemented in only a couple of lines of code. And it lets us progressively solve the interpolation problem, as shown here. If you're familiar with rendering, this algorithm should appear very familiar. Both rendering and walk-on-spheres recursively evaluate integrals by alternating between a geometric query and a sampling decision. Rendering estimates light transport, whereas walk-on-spheres estimates the solution to a Laplace PDE. Like rendering, we need to be mindful of our recursive integrals. So we only prove that the Monte Carlo estimator of a single integral converges, but we didn't say anything about arbitrarily nested integrals. Are Monte Carlo estimates of these integrals well defined? All we need to do is make sure that the integral exists, and then the Monte Carlo estimator will also be well defined. This isn't all that different from checking whether a matrix raised to an infinite power exists. In this matrix case, we can check that the matrix isn't making the vector x bigger with each multiply, since that would cause the solution to diverge. For an integral operator, we have the same convergence condition, except we consider it for the integral operator norm, as shown here. To analyze the convergence condition for the mean value integral, it's sufficient to check that the norm of the integral operator is less than 1. The mean value over the ball, however, doesn't actually converge, since its operator norm is always equal to, but never less than 1. And this makes sense. There's not a termination condition inside of the averaging operator. We just keep recursively evaluating the solution. Fortunately, walk-on-spheres doesn't exactly use the averaging operator. It instead evaluates the solution in the domain and the boundary data in the epsilon shell. The recursive operator, therefore, is only defined over a subset of the sphere outside of the epsilon shell. And so the integral always has a norm that's less than 1. And this makes a lot of sense. By incorporating an epsilon shell, we always allow walks to terminate, and so nested integrals are now well defined. So we need an epsilon shell to ensure that walks terminate, but this doesn't end up being a major limitation. The epsilon shell introduces only a minimal amount of bias, and its exact scale has little impact on performance. So in this GIF, you can see that as the epsilon shell becomes smaller, the number of walks will increase, but only at a modest rate. And the bias in the solution similarly behaves in a predictable manner. So how can we be sure, though, that the same holds true on other domains? Binder and Braverman show that the expected steps it takes for walk-on spheres to reach the epsilon shell is on the order of log of 1 over epsilon, regardless of the domain or the dimension. So in cases where we expect to use a really small epsilon shell to capture fine-scale geometry, walk-on spheres isn't going to experience a massive slowdown. So when you think of where you might use walk-on spheres, you should consider leveraging it on geometry with vast amounts of fine detail that would be computationally burdensome, if not impossible, for traditional methods to handle. By merely decreasing the epsilon shell, walk-on spheres can adapt to fine geometry, whereas a method like finite differences requires the domain to be discretized into voxels that have a scale matching the scale of the smallest geometric features. This requires 1 over epsilon raised to the d voxels, which explodes for sufficiently small epsilon relative to the much more favorable walk-on spheres bounds from Binder and Braverman's analysis. Even though there's a bound on the number of steps for walk-on spheres, though, we still need to consider the computational cost of each step. At each step, we need to find the largest empty sphere around a point, which involves computing the distance to the closest point on the boundary. This is very similar to the ray intersection step that's performed during path tracing and rendering, so there are a lot of ideas and data structures that we can borrow from rendering to ensure that these queries remain scalable. Let's first try to understand, though, what all a closest point query entails with a simple example. So suppose you want to compute the closest point to a line segment from a point x. The closest point is just going to be the projection of x onto the line segment with some extra handling for edge cases where x projects onto an endpoint of the line segment. And here we can denote the distance from x to the closest point on the line segment A as d of xa. If you now have two segments, then the closest point query involves computing the closest point on each primitive, and then taking the minimum of these two distances. For an even larger number of line segments, we have to store the segments in a bounding volume hierarchy, which has an amortized query cost of O of log n. So for a mesh, the cost of walk-on spheres will actually scale logarithmically with geometric complexity. This bounded volume hierarchy approach is very similar to the ones that are used by rendering, so we can borrow heavily from those data structures for walk-on spheres. Beyond explicit meshes, walk-on spheres can also be used on any geometric representation that supports closest point queries. This lets us directly solve PDEs on implicit geometry, like sign distance functions, neural implicit surfaces, or even harmonic implicit surfaces, without an intermediate mesh. And only very recently have scalable queries been developed for some of these representations, and so applications of walk-on spheres to these alternative representations are largely underexplored. Now, let's end this section by taking a broader view of the benefits that Monte Carlo methods for partial differential equations can provide. And many of these benefits are the same ones that we see with rendering, owing to the apparent similarities between these two techniques. First, as long as the PDE that we want to solve is well posed, we can also be confident that this Monte Carlo solver will generate a physically meaningful solution. We don't have to know, for instance, what function spaces we're working with, or what basis functions span that space. The cost of adding geometric detail grows like n log n, and this means that we can scale to problems with billions of effective polygons using techniques like instancing. And just like rendering, we get perfect parallel scaling by averaging results from n different processors. And we can immediately get a progressive and view-dependent preview of the solution by taking just a few samples. Just like rendering, we can directly work with a mix of different geometric representations, like meshes and implicit surfaces, without having to generate a separate finite element mesh. and we get a reasonable solution even if the input geometry has defects, like cracks, self-intersections, and low-quality triangles. So, although there's been renewed interest in these methods over the past several years in graphics, the idea of simulating random walks to solve PDEs dates back to Einstein, who related the random motion of particles described by Brownian motion to the solution of a heat equation and its steady-state counterpart, the Laplace equation. In 1956, Muller laid the groundwork for walk-on spheres, and he observes that as long as the problem is well posed, then we don't actually have to worry about the geometry. Walk-on spheres was reinvented a decade later under the name floating random walk, and then much later, Binder and Braverman give an analysis of its performance and complexity. Over the years, there have been a couple of dozen papers that propose extensions and use walk-on spheres for applications in integrated circuit design and molecular dynamics. But compared to finite element methods, these techniques haven't received nearly as much attention. The main challenge so far has been that walk-on spheres only applies to a limited set of PDEs. In the rest of the talk, we'll show how walk-on spheres can be extended to handle PDEs and boundary conditions beyond the original walk-on spheres algorithm. And in the next section, we'll discuss Poisson equations in particular. Most real-world systems are not determined entirely by boundary data, but instead have sources of heat or electrical potential inside of the domain. So each person sitting in an auditorium, for instance, acts as a heat source. And designing a building or auditorium with efficient HVAC systems requires accounting for these types of source terms in simulation. Similarly, source terms show up in chip design, where wires and components on a circuit board have a significant impact on the temperature of the circuit board. We'll follow a roadmap that's similar to the last section to introduce source terms to walk-on spheres. So first, we'll write down the standard model for Poisson equations. We'll then show how we can express these problems using a Green's integral, and then we'll show how to develop a walk-on spheres extension using these integrals. In the last section, we saw a Laplace PDE that looked something like this. In the thermal setting, we can think of the Dirichlet boundary condition as prescribing some temperature on the boundary, and the Laplacian as interpolating that temperature smoothly on the interior. Now we'll consider the addition of a source term F. This term can be thought of as a heat source in the domain, such as a body that's giving off heat or a really hot component of a circuit board. Because of the source term, the solution U is no longer harmonic, so we can't directly apply the mean value integral like we did before. Let's build some intuition for these integrals and see how we can generalize the mean value integral. If we consider a direct delta source in free space, the solution is a closed form expression known as a free space Green's function. And specifically, the free space Green's function models how heat is transferred from a point z to x as a result of injecting heat at z. We can generalize the free space Green's function to another analytic Green's function on a ball in a similar manner. The only difference is that we've now restricted the boundary of the ball to have a constant zero temperature. If you'd like, you can think of this as an idealized absorber of heat. Since the source terms are additive, we can also model two heat sources in the domain as a sum over Green's functions for the ball. So now the function W represents the total heat at a point x as a result of point sources at z1 and z2. And finally, this can be generalized to an integral where we convolve the Green's function for the ball with an arbitrary source function. So we have a way to describe the influence of a source on the temperature at any point within a spherical domain, and we'll refer to this as Green's integral. The Green's integral over a ball acts as a correction term for the mean value integral, which enables a generalized mean value integral for Poisson equations. We have the same mean value integral as before on the left, which incorporates the boundary data, but we now also have the Green's integral term, which incorporates the effects of the source term within the ball. We already know how to evaluate the first integral recursively. The second integral can be estimated with a single sample Monte Carlo estimator, where z is sampled uniformly on the ball. The walk-on spheres algorithm for the Poisson equation is almost identical to before, except now we evaluate one additional sample in the ball at each step. Overall, the changes here require about 2 lines of code to the algorithm we introduced before. But we're not quite done, however. So far, we've been uniformly sampling the domain, which yields sample points like this. While this is unbiased, uniform sampling produces samples z for which the values of the integrand, g times f, is vanishingly small. Most uniform samples fall away from the center of the ball where the Green's function is largest, or outside the area where the source term is non-zero. And since most samples don't contribute much to an estimate, uniform sampling can be quite inefficient. Instead, we want to avoid sampling points in regions which contribute little to the integral. So rather than sample from a uniform distribution, we can sample from a distribution which approximates the integrand. And to make this unbiased, all we have to do is reweigh the samples a bit according to our distribution so that we can account for over or undersampling relative to the uniform distribution. In our Green's integral case, a simple improvement is to sample from a PDF that's proportional to the Green's function. If we do so, then each sample will contribute more to the estimate on average, and this makes our estimator more efficient. Notice that in the bottom zoom in, there are more points in areas with large values for the Green's function. How do we reason about these improvements in efficiency, though? We can consider the variance of the importance sampling estimator, which is just the average squared distance of the estimator from the true integral. To compute the variance, we use the definition of the importance sampling estimator, apply the homogeneity property to move the constant out front, and use the independence of the estimates to move the variance into the sum. Since each sample is identically distributed, the sum can be further simplified, and we can see that variance really only depends on the variance of this inner term over the random samples. Notice that the only factors that we can control in this expression are the number of samples n or the sampling strategy p. The sampling strategy which will minimize variance is the one that's most proportional to the integrand. So mathematically, we can see now why sampling proportional to the integrand has the lowest variance. But let's see if our Green's function sampling actually improves our Poisson equation estimates in practice. Going back to our test scene, we can see that importance sampling the Green's function on the right does in fact reduce variance compared to uniform sampling on the left. Even though both estimators converge to the same value eventually, the importance sampling estimator converges faster. If we freeze at 128 samples, we can see that importance sampling leads to a much sharper solution profile. And again, at 1024 samples, we see that importance sampling still outperforms uniform sampling, and that uniform sampling actually begins to exhibit artifacts or fireflies due to how poorly it concentrates samples in regions where the Green's function is large. So we chose to importance sample the Green's function since it has a large impact on the integrand, but we can actually importance sample any function that we choose. For instance, we could have chosen to instead importance sample the source term itself. To importance sample, though, we need to be able to generate samples and evaluate the PDF. We don't discuss these methods in detail, but as a pointer, there are two common ways to generate samples. Rejection sampling generates samples from a known distribution and then discards samples proportionally to the target function. And this is the approach that we use to sample the Green's function. The other approach is to transform samples from a known distribution, like a uniform distribution, to some other target distribution. Finally, we often have several sampling strategies we want to use, perhaps one for the source and another for the Green's function. So how do we decide which to pick? Suppose that you're a goalie and you have to decide whether to jump left, which is one sampling strategy, or jump right, another sampling strategy. In these cases, it's often best to use a mixture of the two strategies, where roughly half of the time you go left and the other half of the time you go right. These mixtures are a simple case of multiple importance sampling, which provides a principled approach to building good mixtures and efficiently sampling them.
Okay, so now that we've covered the basics of Monte Carlo and walk-on spheres, let's switch focus to more advanced estimators. So recall that the walk-on spheres algorithm uses the largest empty ball tangent to the boundary to solve Laplace and Poisson equations. However, a big limitation of this algorithm is that it can only handle Dirichlet conditions, which prescribe fixed values on the boundary. But what if we also want to handle Neumann conditions, where rather than interpolating fixed boundary values, we now need to interpolate prescribed derivatives? Neumann boundary conditions are fundamental for a number of very basic applications. In fluid mechanics, they provide the change in velocity or pressure gradient at an interface. In structural analysis, they prescribe the surface traction or stress. And in thermodynamics, they correspond to the heat flux across the boundary. So physically, this means that if the normal derivative is, say, 0 on the Neumann boundary, then this boundary is insulated and heat isn't allowed to leave the domain. Okay, so how can we modify walk-on spheres to incorporate such boundary conditions? Well, because Neumann conditions prescribe derivatives, that means that if we use the slope h to extend the function slightly beyond the boundary, then this extended function will essentially have mirrored values on either side of the Neumann boundary. And so, intuitively, this suggests that maybe our random walks should also be mirrored or reflected across the Neumann boundary. So a naive strategy then is to randomly sample the biggest sphere that crosses only a single edge on the boundary, and to reflect back into the domain if we're outside. The one big problem with this approach is that it becomes super inefficient as the resolution of the boundary increases. Now, we could try using a bigger ball, but if we do this without accounting for the curvature at the vertices, then we'll necessarily have bias in our solution estimate, which negates a key strength of walk-on spheres, which is that it can simulate random walks in a mostly unbiased way. Another option is to just push the random walk back into the domain by a small fixed distance if it enters the epsilon shell around the Neumann boundary. This approach has two problems. First, walk lengths can become extremely long since the boundary serves as an attractor for walk-on spheres. And second, we get a large buildup of bias that accumulates with every boundary reflection since we're effectively approximating the normal derivative with finite differences. So to bypass these issues, we'll have to look for another way beyond just estimating the usual mean value property of harmonic functions. In fact, we'll consider an entirely different integral formulation for harmonic functions called the boundary integral equation. This equation is also sometimes called Green's representation theorem. So, like the mean value property, U is the unknown solution whose value is only known on the Dirichlet boundary. But the BIE actually also gives us a natural way to incorporate non-zero Neumann boundary conditions because it includes the normal derivative of the solution. G is our usual Green's function, P is called the Poisson kernel, and it's defined as the normal derivative of G. It's actually quite easy to derive this boundary integral equation. We start with the Laplace equation and multiply both sides by the Green's function g and integrate over the domain omega. We then apply integration by parts. We now apply the divergence theorem to the first integral, which turns it into an integral over the boundary. We now apply integration by parts again, but this time to the second term. And finally, we use the definition of the Green's function on the left-hand side to get our BIE. The boundary integral equation actually holds for the Poisson equation as well. So here u and du dn are the Dirichlet and Neumann values, f is the known source term, and p and g are our usual kernels. Okay, so now that we have an integral expression, does that mean that we can apply Monte Carlo to Neumann problems? Well, it's not that easy for a couple of reasons. The solution u is not known on the Neumann boundary, dudn is not known on the Dirichlet boundary. We don't yet have a random walk procedure for generating samples, and in general, P and G are not known for any arbitrary domain. So let's address these issues one by one. Now, even though the Poisson kernel and Green's function may not be known for an arbitrary domain, they are known analytically for simple domains such as a ball or free space. In fact, if we assume that our domain omega is an empty ball in this boundary integral equation, then the Poisson kernel is uniform and the Green's function is 0 over the boundary of the ball, which means that we recover our usual mean value property for walk-on spheres. So what this suggests about the BIE is that we don't always have to apply it over the entire domain omega. We can in fact specialize it to any subdomain A. So for a Laplace equation with 0 Neumann boundary conditions, the solution now equals the integral of the Poisson kernel of A times the unknown values at all points on the boundary of A. So think of this equation as a generalized mean value property. The next idea then is to take a walk on subdomains that can contain parts of the Neumann boundary by just repeatedly sampling the Poisson kernel. So notice that we now take large steps away from the boundary, but unlike walk-on spheres, we actually don't yet have a way to pick the next random walk location because in general, the Poisson kernel is not uniform over the boundary of A. But before we discuss how to do that, let's first consider an even more general version of the boundary integral equation. So it says that we can pick any region A and any other region C, and then integrate the Poisson kernel of C over the boundary of A. So this gives us a lot more options. So before we decide on a subdomain A, we'll first choose the region C to be a ball. This is because if we're starting at the center of the ball at a point x, then the Poisson kernel at y is the familiar sine solid angle. So here n is the normal to the boundary at y, dotted with the direction towards y, times 1 over the squared distance from x to y. Intuitively, the sine solid angle is the size of the shadow cast by the boundary on a unit sphere around the point x, and it takes into account the relative orientation of the boundary and the sphere. Some of you might recognize the sine solid angle as the kernel of the winding number integral, which measures the extent to which we're inside or outside of a domain. So for any watertight domain, we can actually compute this integral by simply shooting a ray in a random direction and returning the number of hits in that direction. If the number of hits is odd, then we're inside the domain, and if it's even, then we're outside. The same sine solid angle actually also shows up in the integrand of the rendering equation as the geometry term, where it multiplies the BRDF, the incoming radiance, and the visibility between any 2 points, x and y. Now, in Monte Carlo rendering, we generate samples y on the scene by tracing rays and returning just the first hit, because we want to importance sample not just the solid angle, but its product with the visibility term. But the BIE doesn't have a visibility term. However, like the winding number, we can still importance sample the solid angle by simply shooting a ray in a random direction to get our next random walk location. Okay, so the next question we need to answer is how do we choose a subdomain A for our boundary integral equation? If we choose A to be the entire domain, then we actually have a problem. We'll have to recursively evaluate the solution at every intersection along the ray because the BIE does not have a visibility term. And this is not something that we want to do because then we'll have exponential growth in the number of points that we need to track with each level of the recursion. So we're instead going to let A be a star-shaped region, meaning a region where every boundary point can be seen by the center point x. And because this region is always visible by construction, we'll only ever have one intersection with the boundary if we sample according to solid angle, irrespective of whether we hit a part of the ball or a part of the boundary inside the ball, which is really nice. So altogether, this leads us to the walk on stars algorithm for mixed Dirichlet and Neumann boundary conditions, which is conceptually very similar to walk on spheres. So until we reach the Dirichlet part of the domain boundary, we now find a star-shaped region around xk. So this could be a ball, or more generally, it could be the intersection of a ball with a domain, as shown here. We then sample the next point on the boundary of the star-shaped region, and we keep going until we finally add a Dirichlet value to our estimate, and we then repeat this procedure n times. So the key difference to walk on spheres, as you can see in this picture, is that our random walks can now reflect off Neumann parts of the boundary. So the final question is, how do we find large star-shaped regions which allow us to take large steps? So this turns out to be easy to answer as well. So rather than just finding the closest point to the Dirichlet boundary, as with walk on spheres, we now also find the closest silhouette point on the Neumann boundary and then take the minimum of these two distances. So by the closest silhouette point, I mean the closest point on the boundary where the normals switch from front facing to back facing. Okay, so this might sound a little complicated, but we can actually compute this closest silhouette point pretty efficiently using the same bounding volume hierarchy we're already using for ray intersections and closest point queries. We just need to store a little extra information about boundary normals that encode the orientation of the geometry, which we can do by associating a cone with each bounding box in the hierarchy. There is one caveat with using walk on stars. So near concave parts of the Neumann boundary, the size of a star-shaped region shrinks because the distance to the closest silhouette point goes to 0. So to prevent walks from stopping, we impose a minimum epsilon on the size of the ball, which comes with a performance bias trade-off like the epsilon shell on the Dirichlet boundary. But it's important to note here that the size of a star-shaped region is actually typically much larger even slightly away from a concave boundary. And in practice, we can use local curvature estimates to set this parameter adaptively, which would result in larger spheres and faster runtime performance. So to recap, the final algorithm is actually very simple. We check if we're near the Dirichlet boundary. If not, we find the closest point and closest silhouette point. We then shoot a ray at the corresponding star-shaped region to get our next random walk location until we reach the Dirichlet boundary and add to our total. We then repeat this procedure n times. Notice that the walk on stars algorithm automatically turns back into walk on spheres when there's no Neumann boundary. We have a step-by-step tutorial for building this algorithm up from scratch in 150 lines of C++ code. We've also released a full reference implementation with a number of additional features, such as the treatment of non-zero Neumann conditions, where we pick up an additional contribution h with every reflection. There's also treatment of pure Neumann problems, where there's no Dirichlet boundary to terminate on, as well as handling of open domains and double-sided boundary conditions, such as this example of generating a diffusion curves image on some really intricate geometry. We stress tested this solver on a number of other geometric examples as well. So for instance, here we model oxygen diffusion in a very detailed model of the lungs by solving the Laplace equation with mixed Dirichlet and Neumann boundary conditions. So unlike a traditional grid-based approach, walk on stars actually doesn't require the solution to be computed over the entire domain. If we prefer, we can inspect the solution locally on just a 2D slice. If we try to generate a tetrahedral mesh for FEM, then state-of-the-art meshing tools either end up throwing away important geometric detail within a limited time budget, like the trachea leading up into the lungs, or they require more than 24 hours to get the geometry right. So the point here is that it doesn't really matter how fast or accurate your FEM solver is if mesh generation is itself slow or unreliable. Here's another example, not from a math or engineering textbook, but from a book on baking bread, where they say it would take extraordinary effort to represent such intricate, highly variable patterns in a heat transfer model. So we took this on as a challenge and used walk on stars to simulate how bread will brown under different conditions on a detailed CT scan with 4 million triangles. Our Monte Carlo solver provides a preview faster than a real toaster, demonstrating how physical simulation can be made more like rendering in terms of progressive and view-dependent feedback. Finally, here we have a lizard sunning itself on a rock, where the Dirichlet conditions provide the heat on the rock, and the Neumann conditions describe how much heat the lizard absorbs. We then run walk on stars to make sure that the lizard isn't going to be too hot or too cold. So in this example, we use a polygonal mesh to represent the lizard and a sign distance function for the rock. For the Dirichlet conditions, we call a ray tracing algorithm on demand whenever we need the incident radiant flux density, without needing to compute it ahead of time over the entire domain. So the key takeaway here is that it's not just easy to mix and match different geometric representations with Monte Carlo, but also different algorithms. Finally, compared to other Monte Carlo algorithms like the walk-on-boundary method, where rays intersect the boundary multiple times, we find that walk-on-stars does much better both in terms of variance and bias, especially as the boundary becomes more reflecting. Now, I won't go into all the details behind the walk-on-boundary method here, but this difference in the amount of noise is directly related to our choice of star-shaped regions as the subdomains for sine-solid angle sampling. It's possible that there are other subdomains that allow us to take larger steps and reduce noise even further. But the key point I want to highlight is that it's almost never sufficient to just throw the Monte Carlo hammer at an integration problem. Geometric insights are critical for designing stable and efficient estimators. In fact, even with Monte Carlo rendering, it's no coincidence that we return just the first hit along a ray. As obvious as it may seem, importance sampling both the visibility and solid angle is ultimately what guarantees that the path traces we use today have predictable and controllable variance. Now, of course, both walk-on stars and path tracing have limitations. For instance, they can require some pretty long walks to find their way through narrow features in the geometry. But with Monte Carlo, there's always room to build more efficient estimators that overcome previous shortcomings, and we'll provide an example or two later in the talk. So up till now, we've described how to solve the Laplace and Poisson equations by building Monte Carlo estimators for the boundary and mean value integrals. However, we can also describe these estimators through an entirely different lens of stochastic differential equations and of Brownian motion in particular. In my opinion, this stochastic perspective actually really enriches walk-on spheres and walk-on stars, and more importantly, it helps us build intuition for how we can generalize these algorithms to solve even more problems. So this starts with Kakutani's principle, which says that if we want to solve a Laplace equation with Dirichlet conditions at a point x, then we simulate realizations of a random process called Brownian motion to the boundary, and compute the expected value of the boundary function g at the points where the random walks terminate. We do this by using standard Monte Carlo integration. Intuitively, a Brownian motion is a collection of independent random increments where each increment is sampled from a normal distribution whose variance is given by some time parameter delta t. In the limit of smaller and smaller increments, denoted by dwt, we then get a continuous random path described by Brownian motion. Brownian motion is named after the Scottish botanist Robert Brown, who was the first to use a microscope to study the erratic movement of pollen in water in the 1800s. Then, in the early 1900s, Einstein related this random motion of Brownian particles to the solution of a heat equation and its steady state counterpart, the Laplace equation. And then in 1923, Norbert Wiener provided a rigorous mathematical framework for Brownian motion. The random process he described is now formally known as a Wiener process, and it's a key concept in probability theory. Brownian motion has found widespread use in many scientific applications, probably because it's the simplest mathematical model for events that change randomly over time. It models thermal fluctuations in physics, the dynamics of reaction diffusion equations in chemistry, the volatility of stocks in financial engineering, and even the uncertainty of unknown events in optimal control, such as the wind forces affecting an aircraft. As some of you may know, it's also the noise model of choice in machine learning for image synthesis algorithms like Stable Diffusion and DALI. Now, because of its universality, people have naturally looked into ways for simulating Brownian motion. So the most obvious simulation scheme comes from the definition of Brownian motion itself. For any point wt1, simply add an increment sampled from a normal distribution to get the next point wt2. This numerical integration scheme is called Euler-Murayama, and it's basically an equivalent of forward Euler for simulating Brownian motion in unbounded domains. Okay, but what about geometric domains that are bounded? So here we face a number of numerical challenges. If we take time steps that are too small, then we can simulate Brownian motion accurately but get long compute times. If we instead take time steps that are too large, then we have shorter compute times but large bias from discretizing our random walks. And this bias actually accumulates with every step of the random walk, even if we choose our time step carefully. In bounded domains, we also have additional bias from needing to truncate the final step of a random walk, which can also easily jump from one part of the domain to another because a normal distribution has infinite extent. So it shouldn't really come as a surprise that we can overcome these efficiency and bias issues by simulating Brownian motion with walk-on spheres. So here we observe that a random walk starting at x is actually equally likely to exit through all points in the sphere centered at x because of the rotational symmetry of Brownian motion. And so if we then uniformly sample the sphere, then there's no discretization error at all. Now, Brownian motion isn't the only rotationally symmetric random process, but its exit distribution is uniform for a sphere of any size, whereas other symmetric processes impose additional constraints on the sphere radius. And so, when restricted to a ball, this actually implies that Kakutani's principle is equivalent to the mean value property of harmonic functions, and that we can think of walk-on spheres as essentially an unbiased acceleration strategy for simulating Brownian motion in bounded domains. In fact, this property of walk-on spheres as a simulator of Brownian motion is broadly useful in other application domains as well, such as sampling problems. With the Poisson equation, we have an additional source term f. So here the stochastic picture is that a random walk picks up a background contribution f as it wanders through the domain. Now we can again restrict the domain to be a ball and ask where on average inside the ball a random walk spends its time. We then recover a distribution that's equivalent to the Green's function for a ball, which is known in closed form. Our final integral expression then multiplies this Green's function with the source term inside the ball as usual. Now, more generally, we can leverage this duality between the stochastic and integral perspectives to solve a much broader class of differential equations, where our general recipe is to first find a stochastic representation for our PDE over an arbitrary domain, then to convert it into an equivalent mean value relation restricted over a ball, which we finally estimate recursively using Monte Carlo. In all cases, this whole derivation can actually be explained without the stochastic representation. But the stochastic perspective provides a lot of useful insights, which can be hard to come by if we look at just the integral equations. So, as a concrete example, the insight of performing reflections on the Neumann boundary with walk-on stars comes from Brownian motion being absorbed on the Dirichlet boundary and reflected off the Neumann boundary in the literature on stochastic differential equations. On a 1D half-line, reflected Brownian motion is formally defined as the absolute value of ordinary Brownian motion. This definition also extends to polyhedral domains, where Brownian motion is reflected back into the domain across any boundary face it crosses. We can therefore simulate reflected Brownian motion using standard numerical integration schemes such as Euler-Murayama. But this tends to produce extremely biased results in bounded domains, and it's also very slow even in domains with simple geometry because of small step sizes. In comparison, walk-on stars takes large steps and introduces negligible bias. The stochastic perspective also helps us extend walk-on stars to Robin boundary conditions, which linearly interpolate a PDE solution between purely reflecting Neumann conditions and purely absorbing Dirichlet conditions, as the Robin coefficient mu is increased. We actually use these boundary conditions in the Mars rover example I showed earlier because they describe surfaces that are neither perfectly reflecting, like an ideal insulator, nor perfectly absorbing, like a black body. In general, these boundary conditions provide a more realistic description of physical materials. And Compared to Neumann conditions, estimators for Robin problems are also more efficient because, from a stochastic perspective, they require simulation of partially reflected Brownian motion, which has a non zero probability of being absorbed on the boundary. So, we use this insight to develop a version of walk on stars that has some probability of termination on the Robin boundary, which helps us improve the efficiency of our estimator because of shorter walk lengths. Now, I won't go into all the details, but at a high level, we observe that the radius of a star shaped region should be smaller than the distance to the closest silhouette point on the Neumann boundary, but also larger than the distance to the closest point on the Dirichlet boundary, since intuitively, Robin conditions interpolate between Dirichlet and Neumann conditions. This choice of a star shaped radius then introduces a reflectance function on the Robin boundary, whose value is bounded between 0 and 1. So it naturally encodes the probability with which random walks should be absorbed on the boundary. Okay, so now I'll briefly describe one other scenario where the stochastic perspective really comes in handy. So real world physical systems often exhibits complex spatial variations that affect thermal and electrical conductivity, elastic response, and even the flow of groundwater. It turns out that we can model such fine scale structures using generalizations of the Laplace equation with spatially varying coefficients. So, for instance, we already know that the Laplace equation describes the steady state temperature inside a domain if the temperature is set to some given function g on the boundary. Adding a source term f yields a Poisson equation where f describes a background temperature. We can also control the rate of heat diffusion by replacing the Laplacian with the operator grad of alpha grad u. So physically, the scalar coefficient alpha controls how quickly heat diffuses inside different parts of the domain. Adding a transport term, omega grad u, indicates that heat is now pushed along some vector field omega. So imagine a flowing river which mixes hot water into cold water until it reaches a steady state. And finally, an absorption term, sigma u, acts like a background medium that absorbs heat. So think of a heat sink or a cold engine block. Now, there are lots of other terms that we could add to a PDE, but these already get us pretty far. Okay, so how do we solve these equations? Well, for more advanced PDEs, we actually don't have mean value integrals readily available. But we do still have a stochastic representation that uses generalizations of Brownian motion. So we already know that Brownian motion uses independent random increments sampled from a normal distribution. Adding a velocity term, omega dt, to our Brownian motion gives us a diffusion process, which we can think of as either a random walk with drift or as a deterministic particle with noise. We can also modulate the strength of the random motion using a scalar function alpha. So as alpha increases, things heat up and particles move faster. Finally, random walks can also be absorbed into a background medium with the coefficient sigma controlling the strength of absorption. So sigma doesn't actually show up in the stochastic differential equation here, but it'll be incorporated in just a moment. Now, it's no coincidence that we can use the same symbols alpha, omega, and sigma for both our PDEs and our random processes. These perspectives are linked by the Feynman-Katz formula, which gives a solution to our variable coefficient PDEs as an expectation over many random walks sampled from a general diffusion process. Also, unlike classical integral expressions, this formula handles spatially varying coefficients. So, the key observation behind our approach is that even though walk on spheres cannot directly handle PDEs with variable coefficients, it can still solve problems with spatially varying source terms. We therefore apply a series of transformations that convert our original variable coefficient PDE into a constant coefficient Poisson equation with a recursive source term. So, from an FEM perspective, it might actually feel like we haven't done anything useful. We just shuffled all the hard stuff to the other side of the equal sign. Yet, from a Monte Carlo perspective, we actually now have a way forward because we can recursively estimate both the boundary and source integrals with a walk on spheres algorithm. On the stochastic front, we're now essentially rewriting the Feynman-Katz formula purely in terms of Brownian motion, which we can simulate using walk on spheres, rather than a more general diffusion process. What's also interesting is that the Feynman-Katz formula actually looks a lot like the volume rendering equation, which in computer graphics defines the radiance L along a ray in a heterogeneous medium that absorbs, scatters, and emits radiation. So something like a cloud or a puff of smoke. But if for a second we put aside the physical meaning of these symbols, then structurally the main difference between the Feynman-Katz formula and the VRE is that one requires simulation of Brownian random walks, while the other provides the radiance along a ray. And so, algorithmically, this is really interesting because PDEs can now suddenly benefit from decades worth of rendering research. So, in particular, we take inspiration from volume rendering algorithms such as delta tracking to design volumetric versions of walk on spheres to solve differential equations with variable material coefficients, which allows us to handle scenes with extremely detailed geometry without any pre-processing or homogenization. Actually, from this view alone, the boundary meshes have about 600 million vertices. With even just a single object in the scene, we find that FEM can't resolve the original geometry, the material coefficients, or the PDE solution. Now, adaptive mesh refinement fixes this, but notice that we have 8.5 million tetrahedra, and we need 2.5 hours of meshing time to resolve aliasing artifacts. And that's just on a single model in the scene. Now, some conventional PDE solvers, such as the boundary element method, don't need to mesh the domain at all. But it's worth pointing out that these solvers cannot handle problems with source terms or spatially varying coefficients. To handle these terms, BEM has to be coupled with a secondary solver that requires volumetric meshing or sampling. Unlike BEM, the Monte Carlo approach is robust to aliasing artifacts because it's tessellation independent, and it doesn't have to deal with dense singular matrices either. Okay, so I hope this gives some sense of the type of PDEs that we can solve with walk-on spheres today, but I think we've only just scratched the surface of what equations we can ultimately solve if we keep building. For instance, there's a whole zoo of random processes in the SDE literature that's related to different types of PDEs, including certain nonlinear equations. Beyond the Poisson equation, boundary integrals are also known for the heat, Helmholtz, wave, and biharmonic equations, as well as linear elasticity. And in many cases, we can even just decompose more complex PDEs into a sequence of Poisson equations. But for now, let's switch focus for a little bit to improving the efficiency of existing estimators.
Recall that the error of any Monte Carlo estimator can be measured by its sample variance, which consists of the variance of the integrand f, as well as the number of samples we use to estimate the integral. This means that to make a Monte Carlo algorithm better, we can either apply techniques like importance sampling to better sample the integrand and get less error in equal time, or we can generate samples faster through better software engineering, parallel computing, or some sort of caching. We've already talked a little bit about importance sampling, so let's consider a technique that falls into the second category. A key characteristic of the Monte Carlo solvers we've discussed so far is that they estimate the PDE solution independently at every point in the domain. This makes them easy to parallelize, but since there's no sharing of information across walks, we end up with a lot of redundant computation, especially if the solution needs to be evaluated densely over the entire domain. These solvers also suffer from noise, which is typical of most Monte Carlo algorithms, as shown here in this potential flow simulation in a wind tunnel. So to address these issues, we'll describe a simple boundary value caching strategy that instead takes walks only from the boundary of the domain and then reuses estimates from these walks over the entire domain. In our wind tunnel example, this provides significantly smoother streamlines, and it also works directly with game assets that might have been designed for visualization rather than sim-ready meshes that are needed by finite element solvers. Now, reusing sample estimates to better exploit spatial regularity is not a new idea. We take inspiration from virtual point light methods in rendering, which first deposit radiance values in the scene, and then reuse these cached values to estimate the radiance at each pixel on the camera. To better understand this sampler reuse strategy, let's consider a Laplace equation with mixed Dirichlet and Neumann boundary conditions. As before, the solution to this PDE is given by a boundary integral equation. But unlike walk on stars, we'll now let g be the free space Green's function over all of Rn, which is also known analytically in closed form. So what this equation says is that if we know both the Dirichlet and the Neumann values on the boundary, then we can compute the solution u anywhere inside the domain. To evaluate this boundary integral, we'll construct a Monte Carlo estimator for uniformly sampling the boundary, where on the Dirichlet part of the boundary, we can directly use known Dirichlet data at the points y, but we have to estimate the corresponding Neumann data. Similarly, on the Neumann part of the boundary, we can directly use known Neumann data, but now have to estimate the Dirichlet data. So here's the interesting part. Once we have estimates for these quantities, we can reuse them across any evaluation point x in the domain. Nothing stops us from using the same set of boundary samples to estimate more than one integral in the domain interior. To compute the normal derivative, we estimate the spatial gradient of u using another mean value-like relationship over a ball, where v is the outward normal to the ball. We then dot this estimated gradient with the outward normal to the boundary to get the normal derivative. In practice, we need to offset the samples on the Dirichlet boundary slightly into the domain because the radius of the ball would otherwise be 0. So the overall procedure looks like this. We first uniformly sample a set of boundary points. We then perform random walks using walk on stars to estimate the unknown values of u and du/dn on the boundary. We update our running estimate of the boundary integral equation at each evaluation point inside the domain, and then we repeat until convergence. This boundary value caching scheme is super simple to implement, it's trivial to parallelize, and it's progressive. It also improves runtime efficiency since we only need to perform random walks from the boundary. We find that by reusing boundary samples, BBC also suppresses the typical salt and pepper noise found in most Monte Carlo algorithms because it introduces correlation among different solution estimates. We can actually also use the exact same boundary estimates to compute spatial gradients of the PDE solution, which have far less noise compared to gradients computed using walk on stars. For Poisson equations, we require sample points inside the domain, but we don't need to run any additional random walks because the source term is known. And we find that stratification of samples leads to even better results, just like in rendering, where generating stratified samples on the camera can improve image quality. Now, a unique feature of BBC is that we can focus computation only on local regions of interest. This is quite different from the boundary element method, where we have to perform a global solve over the entire domain. Now, one challenge is that, like a traditional PDE solver, error in the estimated solution is more global, but the formulation is progressive and unbiased, so the error still vanishes with more boundary samples. So overall, techniques like BBC are really just the tip of the iceberg when it comes to reducing noise and improving the efficiency of Monte Carlo PDE solvers. There's still decades worth of inspiration to take from rendering, stochastic control, and even mathematical finance to develop variance reduction strategies that either outperform BBC or work side by side with it. For instance, we already discussed important sampling strategies for source integrals with walk-on spheres, where we can generate samples from the Green's function, the source term f, or a combination of the two via multiple importance sampling. For variable coefficient problems, we can use a weight window strategy from neutron transport to probabilistically terminate random walks with low contributions and probabilistically split walks with a high contribution for better exploration of the domain. Beyond our own work, a number of other research groups have also developed variance reduction strategies for walk-on spheres, such as solving PDEs in the exterior of a domain by spherically inverting the domain with a Kelvin transform and then performing random walks in the inverted domain. This paper applies a really nice geometric insight unique to Laplace PDEs, which yields much cleaner estimates compared to naively terminating random walks in the exterior of the domain. Similar to bidirectional path tracing in rendering, there's also now a bidirectional algorithm for walk on spheres, where we can start walks from the boundary, which make it easier to sample localized boundary conditions and source terms. Alternative caching schemes have also been developed based on a modified mean value property, as well as on predictions from a neural network to guess the PDE solution and terminate walks early before they reach the boundary. These types of caching strategies can be useful in domains with thin features, where both walk on stars and path tracing struggle. So, the key takeaway here is that in general, it makes a lot of sense to design variance reduction strategies that target complementary aspects of a Monte Carlo estimator, because then they can be combined seamlessly.
Okay, so we'll now start to wrap up. So today we've presented an emerging class of Monte Carlo methods based on the walk on spheres algorithm. These algorithms use random sampling to solve some basic but pretty fundamental partial differential equations by framing them as integration problems. Walk on spheres inherits a lot of the advantages of Monte Carlo rendering, which gives it a unique place in the landscape of numerical solvers for PDEs. But it's also not always the right tool for the job. Our own experience in Monte Carlo has been something like this. So we come up with a Monte Carlo estimator for a new PDE or boundary condition, and we're like, wow, Monte Carlo is awesome, so simple and so elegant. We then run our solver on some simple geometry and compare against FEM, and we're like, oh man, this is so slow, so noisy, it just takes forever to converge, and why are we even doing this? And then finally, we run our solver on, say, some complex geometry from TurboSquid, like the Mars rover, and it just works. Super simple to implement, super robust. We only need to compute the solution where we want it. And it's just so much fun to launch a lot of jobs on AWS and get 100 times speed up. And this is because Monte Carlo methods are fundamentally different from traditional solvers, since they're not bottlenecked by discretization and the need for simulation-ready meshes. And being discretization free helps to make simulation more like rendering in terms of progressive and view dependent feedback, and it offers new opportunities for iterative design. In our opinion, there's actually not much value in spending too much time making an apples to apples comparison between traditional solvers and Monte Carlo. It's probably best to just let go of these performance comparisons and to instead focus on the fact that these are very different algorithms with very different potential use cases. Earlier in the talk, we discussed how rendering underwent the same transition from FEM to Monte Carlo methods in the 90s. But there wasn't actually always consensus around the place of Monte Carlo methods in light transport. If we travel back in time to the 90s and read email threads at the time, we see that there was actually a lot of skepticism and doubt around Monte Carlo methods and whether they were worth pursuing. So one person in the thread says, I can't see any advantages of these methods except that meshing is not needed. And there was real concern that Monte Carlo methods were just an academic curiosity. But one response from Pete Shirley stands out. He says that Monte Carlo is so dumb that it doesn't get hit by big scenes, and he also adds that it's easy to implement. The simplicity of Monte Carlo methods is actually not just a convenience when it comes to implementation. It also sets these algorithms up to benefit from any future hardware or computing improvements in line with Rich Sutton's famous Bitter lesson, which says that we should try to develop methods which scale with computation, even as computation becomes very great. So, what's next? Our own work has focused on expanding the class of PDEs we can solve with Monte Carlo by building some basic features. But other researchers in graphics have already started doing some pretty interesting things beyond variance reduction, such as developing full-blown Monte Carlo solvers for fluid simulation, where ultimately the goal is to simulate parts of the fluid that are visible, rather than doing a global solve on a large grid that is mostly hidden from view. There's also recent work on infrared imaging, which provides a unified Monte Carlo framework for jointly simulating the coupled physics of thermal conduction and radiation through a combination of walk on spheres and ray tracing. Building multiphysics solvers that also incorporate convection is an exciting direction for future research. Differentiable Monte Carlo PDE solvers are also on the horizon, where the goal is to solve inverse problems like shape optimization to recover the shape of an object given measurements like temperature or electric potential. These types of solvers can eventually open the door to many real world applications, such as the thermal aware design of circuit boards. Finally, independent developers like Ryan Schmidt have also come up with some pretty creative use cases of walk on spheres, such as agent path planning. So, in this demo, the ball follows the character moving around the scene by computing a vector field only locally at the center of the ball so that it points in the direction of the character. So, to summarize, some of the next steps include extending walk on spheres to more physical problems, going from research to production by developing high performance GPU systems, and coming up with new variance reduction strategies that might involve AI based denoising and supersampling. And finally, being on the lookout for applications where the unique capabilities of Monte Carlo really shine. There are a lot of resources available online if these topics are of interest to you. So we've put these slides up on GitHub. The material that we covered today can also be found in my PhD thesis in a single document. More generally, PBRT is a classic resource for learning about Monte Carlo methods applied to rendering. The CMU course on Monte Carlo methods and their applications covers these topics more broadly, and it's a really nice resource as well. And finally, for a deep dive into Brownian motion, Brent Oxendaal's book on stochastic differential equations is great. And that's it. Thank you for listening.